So welcome everybody. I'm happy to introduce to you Daria Kubyshkina. She is a postdoc in Graz working with Luca Fossati. And just a short overview about her past career. She did a PhD in 2016 in St. Petersburg with Professor Semenov. Then she went to Graz to do a first postdoc working with Luca Fossati and also Helmut Lammer. Then she went to Ireland as a research fellow at the Trinity College Dublin, and now she's back in Graz. And her expertise is ranging from analytical and numerical modeling of exoplanet atmospheres, their evolution, the star evolution, the interaction between stars and their planets, the loss of material from these atmospheres, and how this is interlinked also with the magnetosphere of the planet. So we will have now Daria speaking about her work, and I enjoy the talk. Exactly, the floor.
So thank you for a nice introduction. And my talk today will be dedicated on the evolution of primary atmospheres of exoplanets. I know that the audience today has quite a broad scientific background. So I will start with some introduction just to put you in a context. So to begin, I will describe the population of low to intermediate mass planets. How does it look like, and what mechanisms have likely input into shaping it? Then I will, in more and more details, speak about the atmospheric mass flows, the driving mechanisms, and what is specific about young planets in this term, and what is specific about old planets. Further, I will speak about the connection of the evolution of planetary atmospheres with the evolution of their host stars, which is quite evident, and discuss for which planets the variability in the evolution of the host stars is most relevant. And then I will summarize. So to start, here I show the most famous figures probably in this field. So on the left, we have the distribution of exoplanets, which were discovered in the last decade, which are hundreds and thousands of exoplanets. And the distribution of their parameters is pretty different to what we know from solar system. To start with the first discovered hot Jupiters, which are giant planets in the mass range from 1 to 10s of Jupiter masses, orbiting very close in to their host stars. Plenty of works are dedicated particularly to these planets, but today I will mainly focus on the lower mass planets, the distribution of low to intermediate mass planets with masses roughly between Earth and Saturn, which is highlighted here. It's a rectangle. And this distribution shows a very, very large spread in density and radii, and can be itself divided into two distinct groups, where here you can see the radii distribution. The group on the left consists of dense planets, which are believed to be the bare, rocky cores, or to host only the secondary, very compact atmospheres. The group on the right, on the contrary, is so-called sub-Neptune-like planets. And their low density and large radii suggests that they are likely hosting the voluminous hydrogen-dominated atmospheres. In between, there is some kind of a gap, which is the lack of planets with radii of about 2 Earth radii. And there are a few mechanisms that have likely input into shaping this population. The most prominent mechanism to shape this population is believed to be the atmospheric escaped ran due to the absorption of the host star radiation or due to the own thermal energy of the planets. and surely formation mechanisms. And not to forget, our view can be to some extent distorted by the presence of high altitude hazes. I will briefly discuss each of these points. And to start, what is the concept of shaping this population with the atmospheric escape? It is assumed that all the planets were formed with some substantial hydrogen-dominated envelopes. But some of them have lost it through time. The exact mechanism of this atmospheric mass loss is yet, however, debated and not certain. But the atmospheric mass loss itself was detected for a number of planets, so far mainly in hydrogen lines. And the values of this escape range like between 10 to 8 to 10 to 12 grams per second, which is substantial enough to alter the evolution of planetary atmospheres and therefore the planetary radii. Also, some imprints of the escape can be seen in the populations of different ages. So if you look at the populations of younger planets, you would see the larger fraction of sub-Neptunes, which yet have their atmospheres. However, as I told, the main driving mechanism of this escape is yet debated. So there are plenty of various mechanisms of escape of atmospheric mass loss, including the classic Jeans-like escape, where the most energetic particles escape the gravitational well of the planet, or the disruption of the atmospheres by the stellar winds, like ion pickup and so on. Those mechanisms are more relevant for the secondary atmosphere, so the Earth-type atmospheres or CO2 atmospheres. But for the long-term evolution of primary atmospheres, the most important is the hydrodynamic outflow. And here, the first to be used and predicted long before any escape was observed at all is the atmospheric mass loss due to the high energy irradiation of the host star, in which approach it is assumed that the flux from the host star is absorbed in the atmosphere and leads to its heating and then expansion and therefore the escape. Here, the most used, the most common approach is the analytical energy limited approximation, where I show the most popular shape of the energy limited equation here. The mass loss is proportional to the XUV, X-ray, and extreme ultraviolet flux of the star. The R0 is planetary radii. The nu is so-called heating efficiency, which actually in this case defines the fraction of the flux which was absorbed in the atmosphere. And RXUV squared is the so-called effective radii of the XUV absorption. So what is the main advantage of this formula? It is analytical, which means fast, and it can be easily applied for studying the populations or the evolution of planetary atmosphere, where you need to calculate like 1,000 points along the track. But it has also its disadvantages. In particular, it has the applicability limits as it is based on the range of assumptions, of which the most important is that the atmosphere is tightly bound. So the absorption occurs in the narrow region deep in the atmosphere, which is more or less true. And this air is located in subsonic region, which means it cannot really be applied for the cases of the catastrophic escape for the young planets, but I will come to it later. However, it can reproduce to some extent the existing population. You can see the radius distribution on the left. So it reproduces the peaks of the population through the slope on the right in the radius distance diagram is not exactly as it is. The other prominent theory, which is popular at the moment, is a so-called core-powered mass loss, where instead of the heating from the host star, the main fueling mechanism of this hydrodynamic escape is believed to be the own cooling luminosity of the planet. So in this case, the outflow, hydrodynamic outflow, works similar to the Parker wind and is depends essentially most on the conditions at the photosphere. So to say, this one reproduces the population as well. However, it is also analytical, which is good, but it also has its limitations because it does not account for the stellar irradiation at all. So it is also capable of reproducing the population to some extent with a different slope. And today, actually, the accuracy of our observation does not allow to distinguish between those two mechanisms, which one had the main input into the shaping the population. It is not possible. So to make pause in the atmospheric escape, I come back to other potential mechanisms that participated, and of them, the formation mechanisms are pretty much important because they at least define with what we start. And in these terms, the important parts are the initial core composition and initial mass distributions of the exoplanetary cores, and the atmospheric accretion mechanisms, which essentially defines with how much of the hydrogen-dominated atmospheres we start. And finally, there is a migration both during the protoplanetary disk phase and afterwards, which can mix it all pretty well up. However, few works have demonstrated that if one considers the realistic parameters for protoplanetary disks, it is already possible to reproduce to some extent the peaks of existing population with only formation mechanisms involved, as in Venturini et al. 2020, they were able to reproduce the two peaks of the population with the metal-rich and the icy-rich cores. So they have some problems when including the atmospheres. And the recent work from Lee et al. 2022 have managed to reproduce the peaks of the population with the accretion mechanisms. However, as we know from the observations, the atmospheric mass loss exists, and it is often large enough to significantly change the picture. But this is already something to keep in mind. So even if we believe that the whole distribution was not made up as it was, which likely is the case, the formation mechanisms define where we start our evolution. So knowing the atmospheric escape rates, we can take the parameters of the planet at any specific moment, predict escape rate, predict how the radii change, and so track the evolution. However, we do not know where we start. And here, the most essential parameters for is the initial atmospheric mass fraction, and to some extent, the post-formation luminosity of the planet. The first one, the atmospheric mass fraction, will depend on the mass of the planet. Evidently, the larger planets can accrete, the heavier planets can accrete more atmosphere, and on the parameters of the protoplanetary disk around this planet, such as temperature of the disk, density, and the dust fraction. So in particular, even for the same planet and the same disk, the accreted atmosphere will depend on the position of the planet in the disk. Never forget migration. And even for planets within 1 to 10 Earth masses, the initial atmospheric mass fractions can range a couple of orders of magnitude, which can be important in some cases. I will come back to it later in this talk. The second, the post-formation luminosity. So the initial temperature of the planet can also range in quite a wide range of parameters, but luckily for studying the atmospheric evolution, it was shown in a couple of works that starting with different initial luminosities, different initial entropies, on the right plot shown with different colors, on the central with different line types, is only important for the very first few tens of million years. Because even if not accounting for atmospheric escape, which intensifies for more inflated atmospheres, the more inflated atmospheres, the hotter planets will cool down and contract faster, and they all come essentially to the same track after a few tens of million years. So this parameter is only important if we look at the young exoplanets. And in this case, it is normally possible to some extent to constrain these parameters. So finally, we should never forget that our observations can also be distorted by the presence of hazes or clouds high in the atmospheres, which are capable of visually inflating the planetary radius. I show here the picture from Gao-Zhang 2020, and you can see in different colors that for different hazes production efficiency, the transit depth can look pretty different. So with a lot of hazes, everything will be more smooth, and the radii will be visually larger than for the small haze production. So in this particular example, it can add up to 20% uncertainty to the radii in sense that when I try to interpret it and find out how much of the atmosphere corresponds to this radii, it might get complicated. So for the rest of my talk, I will be mainly focused on the atmospheric mass flows and intermediate mass planets. So as I have already mentioned, the main advantage of the analytical approximations such as the energy limited escape or the core powered mass flows is that they are analytical and fast to calculate. However, their main problem, they have limits of limitation. So energy limited escape cannot account for the catastrophic escape, which is pretty important at early times. And the core powered mass flows ignores fully the input from the stellar part. However, the proper hydrodynamical simulations of the upper atmospheres to define the escape rates are time consuming. So even for relatively simplistic 1D model on one core, it takes a few hours, which is not a problem if we want to study one or a few planets, but in case if we would like to look at the population or at evolution, it is way too slow. So to solve this problem, we have decided that we create a large grid of the hydrodynamical upper atmosphere models for planets that span in the large range of planetary parameters and also the large range of parameters for the host stars. And then use this grid to interpolate within and to get very fast, comparable to the analytical approximations, but more physically reasonable estimations for the escape rates. Here I show you some results which we got with using 1D hydrodynamical model, which assumes the purely hydrogen atmosphere exposed to the stellar heating, where the stellar heating is divided in the X-ray and extreme ultraviolet ranges, and for each taken one specific wavelength at which all the flux in these ranges are emitted. Finally, the model accounts for some cooling processes like Lyman alpha or H3 plus cooling, and accounts for the basic hydrogen chemistry naturally, like ionization and so on. Finally, we employ the constant heating efficiency of 15%, which was shown to be a reasonable estimate for the range of planets we are interested in, so between Earth and Saturn. The grid ranges are from 1 to 109 Earth mass planets, 1 to 10 Earth radii. And we consider equilibrium temperatures from 300 K, so the optimistic habitable zone, up to 2000 K, which is the maximum temperature where we can yet have a molecular hydrogen at the lower boundary of our simulation. And this temperature is bound with orbital separations, with the mean orbital separations for this temperature for the specific given stellar mass. And the stellar masses in our grid range from 0.4 to 1.3 solar mass. For XUV level, we consider about a half of the present sun, up to about 10 to 4 of the present sun to account for the young stars. And this range is scaled accordingly for stellar masses. So finally, to our results, here I show the distribution for the atmospheric mass loss rates against the Jeans escape parameter, which I show here on the right, and it is technically the relation of the gravitational energy of the planet to its thermal energy. And as one can see here, we have two distinct branches. One on the left hand for the low gravity planets, for the hot and inflated planets, and one on the right for planets with higher masses, higher gravity, and somewhat cooler. And on the left, the atmospheric mass loss rates depend steeply on the relation of the gravitational energy of planet to thermal energy. So with increasing relation, it goes steeply down. While on the right side, this dependence is more moderate towards existing. The planets in these groups also behave differently in relation, the atmospheric mass loss rates also behave differently in relation to other parameters, in particular on the stellar input. So below I show in red and in green how those atmospheric mass loss rates depend on the stellar XUV flux. And one can see that for the left group, I will refer to it as low gravity regime and high gravity on the right. So for the low gravity regime, we see only a weak dependence on the stellar XUV. So this suggests that the atmospheric mass loss rates in this case are mainly powered not by the stellar insolation, but instead by the own thermal energy of the planet. The planets in high gravity regime, on the contrary, depend on XUV nearly linearly, as it is the case for the energy limited approximation, which suggests that here the stellar XUV plays the major role. So does it actually mean that our planets on the left are the same as the core powered mass loss and those on the right as the energy limited? It's not exactly the case. So here I show some comparison. In the top panel, it's again the atmospheric mass loss rate against the Jeans parameter. Black points are our escape rates. Blue and green points are the energy limited approximation with different assumptions on the on where the stellar XUV will be absorbed. The green in case if it is assumed to be absorbed exactly at the photosphere, which is often done. And the blue ones where we assumed the effective radii of the XUV absorption as predicted by the Hydra models. The magenta points are predictions of the core powered mass loss approximation as given in Gupta and Schlicht in 2019, and using the photosphere parameters the same as for the grid. So it looks indeed somewhat similar in two regimes, but closer consideration reveals it is more like order of magnitude correspondence, because even in the even in the range of the applicability of energy limited and the core powered mass loss, they would assume that all the absorbed energy is spent on heating and on the escape exclusively, while in reality, it's not exactly the case. So here you can see the yellow points, for example, for energy limited, show that it is overestimation most of the time. I will not stop too long on this one. There is a whole paper written by our student Andreas Kren on this. So if you're interested, you can look in. It's desperately long. And on the left side, it is the black points that give the underestimation, except for the planets where the Roche slope of the planet, so where the atmosphere is at all gravitationally bound to the planet, is located close to the photosphere. So such planets are presented in the grid, and they are mainly in this region of the extreme mass loss rates. Yep.
Can you just remind me the x-axis? So that's the Cheese escape.
It is the Cheese escape parameter.
So it's like an efficient, or yeah.
No, that's here. It is essentially the gravitational potential of planet related to the thermal energy. Thank you. So the planetary mass to planetary radii multiplied by the equilibrium temperature of the essential parts. So to go further, we now have seen that the atmospheric escape rates can differ pretty much for planets of different parameters, like, just to remind, about 10 orders of magnitude. But the question is if for the very same planet, the regime, so the main fueling source of the escape, remains the same throughout the whole evolution. And to illustrate this a little bit, I consider here a few specific evolutionary tracks which are computed accounting for the thermal evolution of the planet and for the atmospheric escape to reproduce more or less two young planets. First of them is Kepler 411b, which is around the Neptune mass planets, around 200 million old, and located relatively far away from its host star, so 0.28 EU. For the exoplanets we know today, it is relatively far. So it is quite massive, it is quite far away, so it is unlikely to experience too much of the atmospheric mass loss through its evolution. So it will mainly be guided by the thermal evolution. It is the green track, and here's the Kepler 411b in this diagram. It is the planetary radii against age. And then we have looked at a few models reproducing the K233b, the very, very young exoplanet, younger than 10 million years, located very, very close into its host star. So apparently, likely very, very much affected by the atmospheric mass loss. Unfortunately, the mass of this planet is not well constrained. It's only known that it is less than a few Jupiters, from the radii, from the radius of the planet, it is most likely that it is not heavier than Saturn, so about 100 Earth masses. Here, I consider a few cases. The one in magenta is one of our reference cases with 30 Earth mass planets starting with the 7% of the mass in the envelope, which reproduces K233b. In cyan, I show the case of 20 Earth mass starting with 10%, but for illustration with unrealistically low initial luminosity. And the other two models I show here, they do not reproduce the parameters of K233b at nowadays, which is, according to our simulation, is likely heavier than 10 Earth masses. It is the yellow and the red line, and they are most affected by the atmospheric mass loss, with the 7 Earth mass planets losing all of its envelope within 100 million years. I show here sometimes snapshots with circles on the way, which are 5, 10, and 100 million years, then 1 gigayear and 5 gigayear, except for the case of the one which has lost everything. So how does it look across our atmospheric mass loss rate diagram? You can see that all planets naturally move from left to the right for increasing gravitational potential, because the planets cool down, contract, and also contract due to losing their atmospheres. And you can see that for all the cases except the very cold start, most of the changes happen within first 10 to 100 million years. Particularly, the large changes happen for the low mass planets, where the change is not only guided by the thermal contraction, as here for the green line, pretty smooth, but also due to the extreme atmospheric mass loss. However, for the first few tens of million years, planets move rapidly across the gravitational potential line, so they contract a lot, and later on they mainly move vertically along the diagram. That means they do not experience such huge changes in planetary radii anymore, but the atmospheric mass loss rate decreases due to the evolution of the host star as the input XUV decreases. And final note to take here is we see that the low mass planets start very much on the left-hand side of the diagram, where the escape is totally dominated by the own thermal energy of the planet, while the heavier planets start more in the transition region, where both the thermal energy of the planet, of freshly formed planet, and the input from stellar irradiation will matter. And for the rest of their lives, the stellar XUV will remain maybe the dominant source. And the final remark, the extreme atmospheric mass loss rates are only existing for 10 to, for about 10, for first 10 million years of the planet's life, which means that it's pretty unlikely that we will be able to detect it. It's statistically unlikely that we see anything higher than 10 to 12 grams per second, which is the case so far. So a couple more words about the young planets. In particular, the atmospheric outflow in this case can be also affected by the interaction with the young star. If in case of the evolved planets, the effect from the stellar wind on the atmospheric mass loss rates will be mainly negligible if we do not come to the secondary atmospheres. In case of the young planets, the stellar wind from the young star will be much denser and much hotter, and it will change. So I show here the case for TOI 942b. And one can see that without escape, everything is quite, without solar and stellar wind, it is more or less smooth and accurate. But with a strong stellar wind, the atmosphere gets strongly confined, and it actually leads to the reduction in the atmospheric escape rate, but not too much, like about twice, which is in the scale of the problem for young planets. Not a lot. It is mainly not so relevant in terms of the evolution. And also the thing to note, for the observations of the young planet, if we want to quantify the escape, it is important to account for the fact that the spectral energy distribution for the young star is not the same as for evolved ones. They are typically much more active in the high energy range, X-ray, and not accounting for this fact in the analyzing climate alpha trends, it can lead to the underestimation or overestimation of the escape a few times.
Can you quickly say something about the difference between the left and the right? It's with and without stellar winds in the 4-panel plot.
You mean this one?
No, the other.
This one. Oh, I did not comment at all. On the left panels, on the top panels, it is without the stellar wind. On the lower panels, it is with the stellar wind, and left is the total velocity, and right is the neutral density. Sorry for that. So to go further, even when the planet evolves and ages, its evolution will be closely connected to the evolution of its host star, as how we have shown before. During the whole evolution, the atmospheric mass flows from the planet will stay connected with the stellar input. So, and the activity, the chromospheric activity, the XUV flux of the star is closely connected to its rotation rate. As the stars spin down with age, the XUV will also decrease, and it goes in the way of the broken parallel. So at the beginning, when the stars spin down very fast, it remains in some kind of the saturation regime, where the XUV is weakly dependent on the on their stellar rotation, and the threshold value here is defined by the specific relation between the rotation period of the star and its convective turnover time. And this relation is also not exactly the same for stars of different masses and colors. So further on, as all the stars are not born the same, but instead they can be born with pretty different initial rotational rates, it leads to the widespread in the XUV luminosity at the young ages, like before 1 gigayear, because the stars which were born as fast rotators will remain in the saturation regime much longer than those which were born as slow rotators. And this also does not look the same for stars of different masses. I show here the figure from Matt et al. 2015, where you see the model and observations for 5 million years and for 500 million years. And you can see that on the right, for the heavier stars, they will get to one track sooner. They will get out of the saturation sooner than those with the low masses. That leads to the value of spread not being similar for stars of different masses. So this early time spread is large for the solar type stars and pretty small for the M dwarfs. And therefore, we would expect to see the most effect of the different stellar histories for stars orbiting heavier stars, for planets orbiting heavier stars. But the most mean thing about this is that if we look at the evolved planetary system, so a few gigayears old, we do not really know what was the past history of its host star. So when we try to model how did go the evolution, we do not really know how it was governed. But luckily, there is a possibility actually to use the hydrogen-dominated atmospheres of planets orbiting evolved stars to constrain to some extent its initial state of the system. So what is important, the early time stellar rotation rate, stellar activity, and maybe to some extent the initial atmospheric mass fractions of planets in the system. So what we need to do that is some kind of the stellar model. In our early versions, we used the simplistic stellar evolution model, which is just a broken power law, setting up the XUV in time. And then this XUV against time is passed to the planetary models, where the important part which we need is some model predicting the atmospheric mass loss rates for the given parameters, which is our grid, and some kind of the interior structure model, which relates the planetary parameters, the observable planetary parameters as radius and mass, to the amount of the actual amount of the atmosphere which it has. For that, in the scheme I will speak right now, we used the relations from the analytical relations from Johnston et al. 2015 and from Lopez and Ford in 2014. So with these two, we can track the evolution of planetary atmosphere for the arbitrarily set initial parameters. But then we can compare it to the observations and see if our initial guess on the initial parameters, stellar and planetary, was correct, and if it hits the present day parameters measured. The accuracy of observations should be good enough, so not more than about 30% on mass and 10% on radii, but this is individual for each system actually. And finally, this procedure is run within the statistical framework, within the MCMC framework. And this allows to resolve the initial parameters of the system in a probabilistic way. I show here our results for the Kepler-11 system. And here in red, I show the priors, which are for the observable parameters, the Gaussian priors. And for those where we have no idea, it's just a uniform prior, like for initial rotation rate of the star or the initial atmospheric mass fractions of the planet. Below, the blue one is our posterior, which is resolved during MCMC run, and the green one is 68% higher posterior density credible interval. So you can see that we are capable to constrain the initial rotation rate of the star, which is compared here with the black line. It is the observations in young open cluster of for the stars of the 150 million years age approximately, and the similar mass to Kepler-11. And we can see that it has likely rotated slower than the average. Finally, for some planets, we are capable of restricting the initial atmospheric mass fractions with which it would be possible to reproduce the present state of the planets. So for some planets, it does not really work, as you can see. It is the case because for low mass or very close in planets, it's often the case that the initial atmospheric mass fraction that does not matter anymore, unless it was too small or none at all. Because however much of the atmosphere you put atop on this planet, it will just escape faster. Because more atmosphere means more inflated atmosphere means more escape. So more atmosphere, faster gone. And it often leads to the fact that with whatever atmosphere you start, you will end up with the same value at the end. Here, the black lines are present day values. So this algorithm can work quite efficiently, and it was implemented in the range of studies to date. You can see, for example, the last paper from Bonfanti et al. 2021, where is the last version of this algorithm, was presented for about 10 systems. But sometimes it simply does not really work. Even though the parameters of the star and planets would suggest that it actually should, because the star is heavy enough to show the large variability at the early ages, and the planets have parameters which suggest for intense enough atmospheric escape. But however, it is the results for TOI 421 system. We can see no actual constraint here. So we were wondering why exactly is it the case, and if we can somehow predict for which planets it makes sense to try our algorithm on for which node. And to test this probability, we have improved our evolutionary models. So if the ones used in the previous algorithm are based on the analytical relations for the atmospheric mass fraction, here we make the simultaneous simulation of the thermal evolution of the atmosphere with the MESA framework, which means the structural models are recalculated every step, and our realistic atmospheric mass loss rate. And here I show some results which we calculated for the small population of planets with masses between 5 and on the top of each panel and 20 Earth masses. And starting their evaluation with various initial atmospheric mass fraction on x-axis from fractions of percent to 30%, which is more or less realistic guess for this mass range. And evolving around different stars. Here I show two left columns, the half solar mass star, and the two right columns, the solar mass star, at different orbital separations. Here I compare not the same orbital separations, but those with similar temperatures, with similar equilibrium temperatures, because it makes more sense for stars of so different masses. And also we looked at stars evolving as fast rotator, so at the top of our stellar distribution, and left column in each case, and the slow rotator, right column in each case. So the first feature which one can see evidently, it is that we see much more difference between slow and fast rotator for the solar mass star compared to the half solar mass star, which we have expected. But also it is the case, yeah?
The color is the amount of atmosphere mass that is lost?
Which is left.
Which is left, okay. Okay.
Yeah, so the color is the fraction of atmosphere which is left. So the blue ones are the planets which have completely lost their atmospheres. So it is at close in orbits, low mass planets. Yeah, it is the evolved planets. It is at 5 gigayears, or at 10, at 5, at 5. But there is not much difference after 3. Another thing to notice here is that we see much more difference. It is particularly well seen here for the planets with more extended atmospheres. So it is pretty evident here, or intermediate atmospheres compared to the compact atmospheres where it evolves similarly. There is also a feature that can be seen here. The distribution shows some kind of the maximum, which essentially means that for planet of the given mass, there is some lucky range of initial atmospheric mass fraction, which allow it to preserve most of the atmosphere. So less than that will be lost too soon. And more than that will lead to the speed up in the escape because of the thermal evolution. So
can you indicate where in the plots you speak about?
Here. If you look at the top, yeah, there is a slope. So there's some kind of the initial atmospheric mass fraction which maximizes the effect, and this effect can only be seen if one looks simultaneously at thermal evolution and the atmospheric mass loss rates, because those two processes are actually quite interconnected because large atmospheric escape leads to faster cooling. Faster cooling leads to faster contraction, and faster contraction leads to the decrease in escape. So they like speak to each other all the time, and apparently if one does not look simultaneously, some effects are to be lost. yes, fun. So also, we naturally see much more difference between fast and slow rotator at close-in orbits compared to the outer ones, where essentially most of the atmosphere is preserved, and the final state of the planet. Here we show the atmospheric mass fraction, but also the planetary radii. It is true. It will be mostly defined by the initial conditions, and so to say, by the formation models in these cases. So it is the case for somewhat heavier planets at closer distances, and most of the planets at the further out distances. I will summarize then. Am I fine on time? Good. To summarize, planets are more likely to be affected by the variability in stellar evolution if they orbit heavier planets. If they are hotter than 500 K and star their involution with more or less extended envelopes. For more distant, heavier or cooler planets, the variability in stellar evolution and actually the mass loss itself might have the less effect than the formation of the formation mechanisms of the planet, and have the larger and have the less the input into the final mass radius distribution. And speaking of the atmospheric mass loss rates, the main driver of the atmospheric escape will likely not be the same for all the planets. It will be the combination of different mechanisms in different proportions for the planets of specific parameters. And it is also likely to change throughout the evolution. When for the very young planet, the own thermal energy of freshly baked planet is likely to dominate the input from the star. And for the evolved planets, it would mainly be run in the energy limited style. So that was it. I'm happy to take the questions.
Thank you.
Thank you for your attention.
Thank you for your talk. Are there questions?
Yeah, so during your entire talk, you always spoke about like the mass loss rate simply as like one scalar, basically. I'm just curious, do the mechanisms affect certain chemical species more than others? Or, for example, does it change the metallicity of the atmosphere?
Well, it actually can, because the heavy elements can be dragged out with the hydrogen escape. But what we have in these models I was speaking about, it is mainly simply the hydrogen escape. So, but yeah, but it can increase the metallicity of the planet over time.
I had a question about the energy limited model where you the efficiency of 15%.
15% is for our hydrodynamical models.
How do you test this?
Well, it was tested with more sophisticated models because the heating efficiency can actually be calculated simultaneously because it basically the heating efficiency in the general sense means the fraction of the absorbed radiation. So the radiation from the star is absorbed by the neutral atoms. It ionizes them. There are some energetic electrons running away, and this all bubbles. So the secondary electrons of this reaction can be spent on heating of the species. It can be spent on the secondary ionizations and so on and so forth. And to account for all the complicated chemistry, it's actually time consuming. Since the grid consists here out of like 10,000 points, it would be like and altogether, I would say it took about a year to complete. With accounting for the heating efficiency, it would take time. So we used some estimates which were made with more sophisticated models for the sub-Neptune and Jupiter-like planets. Particularly, we took the one from Salz et al. 2015, which is the combination of the hydrocode with the complicated photochemistry code, the cloudy, which is, yeah.
So maybe you said it and I missed it, but what role do magnetic fields play in all of this?
The magnetic fields here do not play any role at all. But yeah, there are surely plenty of studies which look at magnetic fields as well. And what we can conclude out of them, there is nothing conclusive. Because the magnetic field effect, it can also reduce the escape by binding the energetic, the ionized part of the particles to the planet. But in some cases, it can also intensify the escape because of the outflows through the polar regions. So that's not a very straightforward thing. Also, people with different approaches come to quite different results. The thing to say, it's most likely will be relevant for the secondary atmospheres and on the contrary for the Jupiters and less for the planets in between. That's more like my impression from all the papers I have ever read and all the simulations I have run myself.
There's a question.
There's a question from the Zoom that I just repeat. So what do you think about the possibility that the atmosphere will be disrupted by impacts of planetesimal? So the hydrogen helium will be just blown away during formation by a series of small impacts?
Well, I prefer not to think about it too much. But in reality, well, we don't really take it into account. We assume that all of this stuff was happening during the early evolution of the system, during all the mess. All the impacts were done at the early times, and we start after all the formation, all the funny stuff is already done. So in some cases, we can say that this planet, for example, there are a few examples, a few outliers in mass radius diagram, which had to start with surprisingly low atmospheric mass fractions. I would have to look at my notes to remember the correct names. But when the Neptune mass planet starts with something like not more than 10% in the envelope, it would suggest that there was something puzzling about its formation. For example, the atmosphere could be removed by such impact, or simply the planet have formed in some material poor region. So during to opening the gap in the disk or whatever. But we do not really go into too much details. It's not my topic. So it's all pretty interesting, but unfortunately you cannot be expert on everything.
There's no more questions.
Well, someone is just raised their hands and I had to type your questions in the chat, so maybe they're typing.
Okay.
Could you comment on why intermediate planets like sub-Neptune planets would be less affected by their magnetic fields, or that magnetic fields play a less important role for the atmospheric mass flux? Because you mentioned it's mainly relevant for Jupiters.
Well, this statement is essentially, as I told, my impression on reading and modeling, but I would say that in general, the Jupiter mass planets, they have stronger magnetic fields. And the small ones, there are different atmospheric mass loss mechanisms which are important. So as I told in the very beginning of the talk, for them, the genes-like escape or ion pickup becomes really important. And those are the processes which will be affected by the presence of magnetic field. While for the intermediate mass planets, the magnetic fields are not expected to be too strong. And also the main escape mechanisms, it is the hydrodynamic outflow. So it would have some effect, but as I told, it will be a little bit uncertain. It depends on which part wins, the keeping of the energetic particles inside or the intensified outflow through the polar gaps.
Oh, now we have the question. So, I mean, time-wise, we're fine. So, excellent talk. Can you please comment on how hydrodynamic escape may also be significant to shape the bulk composition, i.e. not only atmospheric composition of the planets during the formation process? Thank you.
Whew.
Should I repeat?
No.
Because there were parentheses. I cannot destroy the sentence.
I'm slightly puzzled because the formation process is not exactly my topic. So, well, the bulk composition will surely be changed due to the escape of the lightest elements. But it's not that straightforward because the heavy elements will be also dragged away. So that's a little bit too large scale question to answer.
It's more common on this because I mean, I'm also an expert, but generally it's not that simple, right? Because if you can build for giant planets, it's not clear if the planet is fully mixed, right? So if the atmosphere even influences the material is not obvious, I guess. But then depending if you have like in situ formation or migrating planet or something, I guess, yeah, I think it's not a easy thing to answer.
No, not really.
I think that's all from my side.
Okay, perfect. So if you want to ask Daria in the afternoon, feel free and just come to me, then I can list you with the people who want to discuss with them. And otherwise, yeah, thanks a lot for the seminar. Yeah.
Thanks a lot for your attention.